Yeah, thank you, Ray, for the introduction. Earlier, I think one of the presenters said that in the ancient times, MTS had this program and mentioned Benson Ching and the program that they wrote, so I felt really old. But I would also like to thank MTS and University of Minnesota and the Mass Lab for inviting us to this seminar and to give this talk. Microphone. Okay, now? Okay, thanks. All right, so I was tasked to talk about hybrid testing and geostructural engineering applications. And I will be mainly focusing on soil foundation structure interaction and hybrid tests in that area. So since the inception of hybrid tests, and the first ones to be developed were fluidodynamic tests, the predominant focus was testing of structures. And typically then dynamic loading on those structures was directly applied at the base of the structure, and then structure was modeled and analyzed and evaluated. The performance of the structure was evaluated. Of course, the performance of the structure actually heavily relies not only on the characteristics of the structure, but characteristics of the medium in which it is embedded and characteristics of the foundation system. All of them, of course, interact with the type of excitation that's applied to that system and affect the result. So here is briefly what are the types of tests available for testing soil foundation structure interaction effect. So one of the oldest ones is centrifuge modeling, and we've heard some of the centrifuge modeling issues. Of course, it's the scaling effect that really governs all the problems that come out from a centrifuge modeling. Then shaking table tests or laminar box tests, where the sample is definitely larger than in the centrifuge, but we still have scaling effects. There is also field testing, not as often done as we would maybe like to. One of the examples that I wanted to mention is this test structure at the Gardner Valley Downhole Array Research Site in California. It belongs to the UC Santa Barbara, I think, and it's this nice one-story simple structure that is resting on the ground. There is a foundation slab, 4 columns, and the top slab. The whole site is instrumented, and the structure itself is instrumented. And it's exposed to natural earthquakes. It's in the earthquake-prone area close to Pool Falls. So they record natural events and measure the response of this soil structure system to those events. Nearby, 3 kilometers away from the site, there is the measurements are taken at the rock outcrop, so we can compare what's measured at the rock outcrop at the same time when these other measurements are taken. And then finally, there is hybrid testing of soils and structures, and all of these above can basically be used in the context of hybrid testing. We've also heard what are the benefits of hybrid testing, that it reduces the cost of the simulation because we decouple basically or partition our system that's tested into numerically tested and physically tested. Then further, with this hybrid testing, there are majority of hybrid tests are really single-site hybrid tests, but there is maybe resurgence of distributed hybrid testing, which is beneficial to soil structure interaction problems because the size is important there, and then limitations of the actual lab facility is overcome by using multiple sites and testing, let's say, structure at one location, foundation at another location, or partition the structure and test it at different facilities. So here is an example of on-site hybrid testing, and the two natural modes would be to partition the system into a, let's say, physical mode that represents the structure, and another physical model that represents the structure, and then numerical model that represents foundation, soil, system, or the opposite, to a numerical model of the structure itself, and then physical model of the foundation soil system. Of course, there are other possible combinations of these systems depending on what is known about behavior underground, what is the size of the foundation structure, and so on. Here is an example of the first method that's shown. So foundation soil system is physically modeled, and then the superstructure is modeled numerically. And the beauty, of course, of the hybrid structure is that now we can do parametric studies and vary type of the superstructure that we have on top of the soil with this type of foundation. So this is the test that was done at University of Buffalo, 23 feet high laminar box. The soil was saturated, so they were trying to evaluate the liquefaction potential at these various instantiations of the test. And the piles themselves were explicitly modeled as well, of course, soil. The interaction between the tested structure and the numerically modeled structure was done through this shape table that's placed on top of the foundation slab. Here are some pictures from the experiment. So we have this laminar box and the shaking table on top of the whole foundation system. This is the foundation system before the shaking table was placed on it. It was instrumented. All 6 piles were embedded in the soil, and here is placement of the shaking table on top of the foundation system. Here is an example of the second method where another approach is taken. So numerical modeling was taking care of the foundation soil system, and this bridge was modeled in reality. The bridge was still scaled, so the tested model is still smaller than the bridge in real life. And the tests were done in Beijing, in China. Here are the authors of the paper where I took the photograph from. And here is conceptually what was tested. So each pier of the bridge was tested on. It had its own foundation system. They assume they have a system of piles that is transferring the load to the medium itself. And here is where they explain how the simulation was done and how was the soil structure system model. solid foundation system model. And those are examples of the on-site systems where everything is done at one site. So numerical simulation as well as the testing is done within one lab. And here is the example of the geographically distributed hybrid test. It was done in England, and it shows the tested structure. It's a 5-story structure. Part of it was numerically analyzed. Part of it was physically tested. These 2 stories were tested at one location. Bottom story was tested at another in Bristol. And then there is here a foundation pad that was tested at the Cambridge University. So this is not a real structure. They were not trying to simulate the real structure. It was more a proof of a concept test. And of course, with centrifuge, the effect was that the time has to be scaled, so the test could not be done, of course, in real time. But they learned a lot from this test, and following this test, they did a successful test that was also geographically distributed. It was done at 2 sites, and a similar structure, it was a 3-story structure, was tested at these 2 sites, and then a numerical simulation was done of the bracing system at the base of the 3-story structure. So, okay, now I will talk about the company that I work with. I don't know why are these effects coming up, and in particular about the software that we develop. And I will do that because we're evaluating the possibility of linking our software and allowing and using it in the hybrid testing environment. Try to go back. So we are based, we are based in Minneapolis. The main office is in Minneapolis. The company was created 35 years ago. Here is geographically where other offices are located, and we have 16 consulting offices throughout the world, and then we have a series of agents that sell our code. So in our history, this trinity of consulting, software, and research was continuously applied, and it kind of fueled our development, and this potentially development would fit into that category as well. Here are some fields where we do consulting in. So rock mass characterization is one of them. We do a lot of work for the mining industry, for open pits as well, underground mines. And in our consulting, we use, of course, our code. And here are some examples of the models that we do. In mining industry, majority of our models are now really million grid points or millions zones models. We do have projects in the environmental engineering area. Here is underground mine design. I was hoping to skip actually these, which go to software, but maybe it's okay if you see these slides as well. So mass mining, whether it's caving or various other methods of mining, we not only model those processes, but also develop special software that facilitates modeling of those processes, and usually mining consortiums really contact us to develop those tools. We do these special software development for the mining industry, but as well, but also for the petroleum industry and some other industries as well. So here is an example of blast engineering. We did a special program that could predict how the mock pile will form what will be the distribution of the fragments that are displaced, knowing what is the charge, what is the explosive strength and positions of those. Okay, so here is where we come to our software. So this is the list of all software that we produce, but we will focus on the ones that are in the blue outlined area. So in particular, FLAC and FLAC 3D, that's one platform. It's a continuum type of modeling that we do with FLAC and FLAC 3D. Then UDEC and 3DEC, that's distinct code, and then PFC. PFC is now a suite. It merges 2D and 3D together. It's just an option that you switch when you want to, when you start modeling. So here are some examples of, first of all, continuum code. So FLAC is a two-dimensional continuum code. It models the behavior soil of rock or rock. We have about 16 built-in constitutive models in FLAC. It allows, we have fluid flow modeling. Structural elements are, of course, part of the formulation. They interact with themselves and with the medium itself. All of the codes involve dynamic modules, so all are capable of reproducing, doing dynamic simulations. And here are some plots of applications of what we've done when using FLAC in consulting. A 3D version of the same code is FLAC 3D. That's our major, the code that we do majority of consulting with, in addition to maybe 3DEC, and we'll talk about 3DEC later. So it has similar characteristics as FLAC 3D, but it's extended to 2D. You know, your computer is different than mine. I never have this problem that it creates these effects. Here are some examples of FLAC 3D models that we have worked on, some underground tunnels and subway stations. Here is, see if this will work now. This should be a movie if it ever starts working. Oh, QuickTime is not available. So of a blast that we have in the middle of this tunnel. So it's a 3D simulation. We have a pressure pulse that models an explosion, and then we could see how this wave propagates and radiates from the site where the explosion occurs and dissipates into these absorbing boundaries on the side. Stress concentration in the other example, and an open pit example. Here's more models that are done with FLAC 3D. Probably not as other things. So those are continuum codes, and then we have the ability to model discontinuum, really, and transition from continuum to discontinuum. This particular code is UDEC, and the simulation here that I wanted to show you. So all these blocks are at the beginning. They're cemented and they're joined to each other. And the red region is completely a continuum region. And then we apply dynamic excitation, and there's unraveling of the blocks. They naturally fracture if the fracture condition is reached at the particular joint. And then we can see them falling down and filling this tunnel. Okay. Now, so that's a discrete code that can really measure, accurately model fractured rock mass. It can model flow through the fractures or through the matrix. Thermal creep calculations, again, are all dynamic. They're all available in all of the platforms. Some examples where UDEC was used in real-life examples, and that takes us to 3DEC, which is similar to UDEC but extended to E. Some examples of the models that we've done with 3DEC. We have even created earthquakes with 3DEC. We do projects for the nuclear waste industry where analysis times are about a million years. You have to prove that the repository or depository is stable for the million years. And there's always an issue of what an earthquake simulate or earthquake excitation should be. So geophysicists usually come up with statistical data and different models to give us these records that we then apply to the model. But in one case, they just gave us the magnitude and asked us to generate the earthquake itself. So we created a huge 3DEC model with the fault in the middle. It was like 60 kilometers and then 50 or 60 kilometers wide. So it was a box, and we caused the fault to slip. That slip was propagating radially along the fault. Earthquake was created. We calibrated the model to fit certain magnitude that we were given, and then analyzed stability of that repository due to that generated earthquake. These were all, or some of these plots were a nice movies to illustrate the capabilities of the software itself. Also, discrete fracture networks can be generated for these models. We use that for geothermal applications, as well as we can impose really any fracture network that you have a DXF of into the model itself. Okay, and this takes us to another form of the distinct discrete element, that's particle flow code, PFC, that we have. With PFC, really, the base is that you go almost to the grain size, even though not completely, but you model these balls and interaction of the balls with each other, and you calibrate this artificially created material to match the, let's say, UCS test, and then use those parameters that you achieve through calibration to build this material. So it's conducive to testing new materials. It's also conducive to doing other simulations. Here is an example of the rock fall that was simulated with PFC. PFC balls can be grouped into clumps as well. They can also be merged to simulate continuum, even though they are naturally discontinuum code. I will skip this. This is a grid generation tool. Here are some special purpose codes that we developed, and blow up is the one that I briefly talked about that predicts muck pile formation and distribution of the particles that are displaced. Rebop is another one for this particular type of mining where you undercut below the ore and then cause fragmentation from underneath and then collect the material that fragments and move further in a controlled way. And so the rebop is used to predict this controlled way of moving through the extraction of the ore. Then synthetic rock mass, that's another PFC-based application. The last one is Excite, and we are now even selling Excite. It was developed for the petroleum industry. It's based on the lattice method, and here we have an example of the horizontal borehole and injection points through which the fluid is injected to stimulate the further hydrofracturing and then simulates the production. All right, so the reason I talked about our codes is to give you an idea of what type of physical behavior can be modeled with them, and we would like to see this distinct and discrete ability to model these types of behaviors integrated into hybrid testing. Again, all of our codes include groundwater flow, structural elements, not only linear elements. So, I mean, by that I mean beams, cables, or piles, but also plates and shells as well. And again, shells and plates and everything that interact with the medium in which they're embedded. Gravity magnitude and the direction is an input parameter for us. So simulations in different environments or in centrifuge environments are very easy to be done, and because all the body forces are automatically scaled. And all the codes, again, they have dynamic analysis, creep, thermal simulations. Now, all the codes themselves are also hybrid, so they can interact with each other. And had this movie worked, I would have shown you the simulation. This is a coupled simulation. So the interior is modeled with CFC, with balls. The interior is discrete, and then it extends to this continuum model that's continuum material that's modeled with Flux 3D. We have a wavelet in the area of it that's modeled with balls, and the wave radiates from that area, and you can see how it doesn't have any disturbance as it flows from the from the discrete medium to the continuum medium. So in a way, it would be natural for our codes, since they're talking to each other, to talk to the physical system, which is then hybrid. And then in summary, we can say that really hybrid testing offers vast possibilities for evaluation and performance of soil foundation and structure systems. Some of the ways to enhance the testing and on the physical side are these geographically distributed hybrid tests that can utilize either expertise or physical equipment that's available in labs to facilitate testing of larger specimens. And then potentially on the numerical side, we could include other ways of modeling the medium and enhancing physics that modeled numerically. That is all. Thank you.